the Exun Talks. Greetings, everyone. Greetings, everyone. Welcome to Exun Talks. I am Duldab Biswas, and I would like to welcome you all. So, Exun Talks are a series of interactive webinars and talks during the Exun Week. These are conducted by professionals across a truly dizzying array of topics and of different types, from game development to the future of automation. With constant interaction, it is a fantastic experience for everyone involved. Today we have with us Tushit Jain. After completing high school from DPS Akipuram in 1998, he pursued his BTech and MTech degree in electrical engineering from IIT Madras. Since 2003, he has been working in the semiconductor industry where he built hardware, software, algorithms used in products ranging from smartwatches, cameras, RFIDs, Wi Fi routers, and POS devices. In 2014, he was the CTO and founder of MagnetWorks, a startup working on industrial IoT solutions for remote monitoring of industrial equipment and processes in factories. After closing his startup in 2015, he returned to the semiconductor industry, where he built and managed teams working on VR and AI. So today, sir will be talking about some interesting problems hardware engineers come across and how to solve them. So,
Develop are the slides up?
uh,
Okay,
yeah,
thanks.
the slides.
Okay. So yeah, I thought I'd give you guys a background in what kind of work an electrical engineer or an electronics engineer does. And of course, a lot of that is hardware design, but there are all sorts of algorithms and hardware problems uh, involved in sort of building electronics. And um, I've spent most of my life in the chip industry that basically builds the chips that go into electronics. So I'll talk about some of the problems, the kind of work that is done in the field, and feel free to ask questions on chat. And if there are any uh, uh, interesting questions, then I'll also try and keep answering them as we go. Yeah, so I started my career in 2003 with a company called National Semiconductors. This was in Bangalore, and one of the first projects I worked on was a chip for the world's first smartwatch. So in 2004, about I would say 10 years before Apple launched its smartwatch, Microsoft actually built a smartwatch with companies like Fossil, Swatch, and a bunch of other watch manufacturers, and the smartwatch was launched in 2004. Uh, it had some very basic features. In those days, you didn't have cellular data connectivity, so Microsoft actually built a uh, FM network, a digital FM network to send updates to the watch. So you could get weather updates and stock updates and news on your watch. It, but unfortunately, you could only do one-way communication. So you could only get updates to the watch. You couldn't send anything from the watch. You couldn't reply to messages. So um, the watch wasn't very successful, but I got to work on the chip that went into the watch. So National was actually building the chip for the smartwatch. And that was one of the first projects I worked on, which was essentially for testing this chip in the lab. When it used to come back from the fabrication plant, it would come to the lab where I worked, and we would design PCB boards to test these chips on. So we'd put these chips on PCBs and write software that would test the processor, the cache, the memories, all the USB interface, the serial ports, all the different interfaces of the chip. We'd write the code to test them. And if there were any problems, we'd debug them in the lab using, software and electronic, measuring devices like oscilloscopes and logic analyzers. Um, and debugging chips is really fun because it's almost like solving a murder mystery. So if you enjoy debugging software code, debugging hardware is, I would say, even more challenging, because it's not just can your software be wrong, at the same time your hardware could be misbehaving, or be wrong, or your PCB could be bad, or the chip might be overheating and therefore not functioning correctly. So there are all sorts of problems that could be happening on the chip, and you have to debug them using software that you write that runs on the chip. And it's one of the most interesting areas for me to work in. And I still remember the days when I used to work in the lab, and I just enjoyed that the most. During this time, I used to spend almost 90% of my time in the lab, running tests on these chips. I learned to solder components on a board. So using a soldering iron, I'd have to sometimes put components on the board or take them off, try various combinations, and things like that. So this was a really fun time of my career. I got to learn a lot, because when you're debugging a chip, you get to learn about everything that's going on in the chip. So you get to know the chip completely. Um, this was also a time where I learned a language called Verilog. So a lot of you have written code in software in programming languages like C, C++, Python, Perl, or JavaScript. But there's another language called Verilog, which allows you to write hardware. It allows you to describe the hardware that you want to build at a very low level. So you describe the hardware like counters or adders and multipliers, and then that code gets, just like software gets compiled to a binary format, this low level hardware description, when you compile it, it gets converted to Boolean gates. So your AND gates, NOT gates, NAND gates, XOR gates. So Verilog is kind of the de facto industry standard of writing hardware description, or designing the chip. So a lot of the chip design actually happens in languages like Verilog or VHDL. Another interesting project I worked on was essentially RFID tags. So, 2004, these RFID tags were very cutting edge technology. They're little chips that have, most of this tag is actually an antenna. The chip itself is like a salt, like a grain of salt on this tag. And this is what essentially, when you cross the toll booth, the fast tags that you use today, we were building tags like these in 2004, and the application was to track luggage at airports. So if your bag gets lost and you don't know which airport it's at, these RFID tags would have helped track them. I think in terms of the things you do at school that are very similar, if you've worked with Arduinos, if you've learned to program Arduino boards, microcontrollers, or or enjoy robotics, then this is the kind of work that you would also enjoy. So that's, I think, the closest parallel in terms of the work that I did at National to kind of things you might be doing at school today. Um, if there are no questions, then I'll move to the next slide. And feel free to put questions in the comments. I'll try and answer them as they come. Then the next phase of my career was essentially working for a company called Connection Systems. There I worked on signal processing algorithms. So when you have communication protocols like Ethernet, or networking protocols like Ethernet or Wi-Fi, there's a lot of what we call signal processing, which is essentially the process of converting the at the lowest level, any data packet that you're sending over a data network is a series of zeros and ones. But even below that level, those zeros or ones need to get converted into some sort of electrical signal, some sort of waveforms that can go either over a wire. In the case of Ethernet, they're going over a wire, or over air in the case of Wi-Fi. So these sine waves or these electromagnetic waves that are going are essentially an encoding of the zeros or ones, and they're essentially like a combination of sine waves and cosine waves. And as part of the work, you try and convert from the zeros and ones to these electromagnetic waves, and then at the receiver of the packet, at the Wi-Fi card or the Ethernet card where the packet is received, you have to take these electromagnetic waves and interpret them back into zeros or ones. And a lot of that work actually involves a lot of math. So if you enjoy math, if you enjoy trigonometry, algebra, calculus, then you might enjoy this kind of work. It's essentially about taking all these waveforms and converting them into zeros and ones. So there's a lot of math involved. There's a lot of simulation of the math. So you take this math and you write it in MATLAB, which is another programming language used for scientific computing, and you simulate this math. You see how would you still be able to decode the packet if there was noise coming in, or if there were two parallel transmissions happening and they were interfering with each other, the electromagnetic waves were interfering, would you still be able to decode them into zeros or ones? So that you write a lot of these simulations, you write a lot of algorithms to debug these waveforms. So, for example, when a Wi Fi packet is transmitted from a Wi-Fi router which is very far from you, just understanding whether there is a packet on the air or not is a very complicated algorithm, because the energy of the packet as it gets transmitted, and by the time it reaches the receiver, the energy might have dropped to 1,000th of what you transmitted with. So a waveform that looks, of say 0 to 5 volts waveform, by the time it reaches the receiver, it may be only 5 millivolts. And so even detecting that there is a packet on the air that you have to decode is a very complicated algorithm that one writes. So there's a lot of these kind of algorithm work that you do in signal processing. Then I even worked on taking these algorithms, implementing them in MATLAB, verifying that they work under all sorts of noise conditions, and then converting those into a Verilog hardware description that can then be used to create a chip out that can perform this math. So a lot of this work is also taking that math and implementing it in hardware in terms of Boolean gates, in terms of AND gates, NOT gates, OR gates. And the other thing that you do is you test the functionality of these chips before you send them to fabrication. So a lot of simulations are done, because the cost of fabricating a chip today is very high. It can be of the order of $10 million or $20 million. So you can't afford to have any bugs. If you have a bug in a software, you can release it again the next month. You can fix the bug, and in the next release you can release the fixes. But in hardware, if you even have one bug that needs you to fabricate the chip after fixing it again, then that can be you can have you could have a cost of 10-20 million dollars just to fix a single bug. So testing these chips before you send them to fabrication is extremely important. um, I have a couple of questions here. What do you believe is a good starting point to delve into Verilog? I think you can get started if you're interested in Verilog. There are lots of tutorials online. You can write simple things like uh, just circuits to add two numbers, or counters or timers, and get started with that. There are also little chips. There are also chips called FPGAs, which are field programmable gate arrays. They You can get simple FPGA boards for about 5 to 10,000 rupees, and you can actually implement your Verilog hardware on those FPGAs and try it out. So you can connect it to an Arduino, your FPGA board. You can create signals on the FPGA board that the Arduino could read, or things like that. So uh, there's um, there's a lot you can do with Verilog and FPGAs, even by doing some basic tutorials online. So I think that's a great starting point. There's another question. Risk-based CPUs, we tend to have things like NOT gates, AND gates, uh, which are generally toggleable. Are such things also present in CISC-based CPUs? They're of course present in CISC-based CPUs. They're present in so AND gates, NOT gates, NAND gates. They form the basic building blocks of any electronics that you see today. So your not just the processor, your Intel processor or ARM based processor, RISC processors, CISC processors, but even your hard disk will have a little controller that controls um the SATA interface. Even that has AND gates, NOT gates, OR gates. Your smartphones, every chip on the smartphone will have these kind of gates. They're the basic building blocks of any chip. So any chip that you see on a PCB, whether it's your Arduino board or any digital circuit, is basically consisting of these gates, and these CPUs are just constructs made out of these and not NAND gates. There's another question. I guess, what made you get into the field of hardware? That's an interesting question. I think I was, of course, very enthusiastic about software when I was in school. Programming was something that I enjoyed a lot. um, I think getting into electronics is partly sort of by choice, partly by what JE rank you get. So there's no good answer to that. But I think the cool thing about doing hardware is that you get to build things. I think you get to build physical things that are just very, very, very cool. Just give me a second. I need to be back. Just I would say that doing building hardware is or studying electronics is actually to some extent a superset of studying software or computer science. When you get a degree in electronics, you also understand the fundamentals of computer architecture. You understand the basics of the hardware on top of which the software is running. So in a sense, it gives you more fundamental understanding of software as well. um, there's another interesting question from Siddharth. What is the most common error hardware enthusiasts make? That's I don't know if there's a common error. I mean, I've made mistakes where I've burnt boards, literally had smoke and fire on top of a PCB. There's I've seen errors on the chip itself um, where I think if I was to categorize them, the most common error is the error of communicating between two people. Somebody writes a spec in one way, somebody interprets it in a different way, and then when the two pieces work together, they kind of fall apart. So that's probably the most common sort of problem I've seen, that people don't they assume that they have understood, or people have understood one thing one way, and somebody else may understand the same thing in a different way, and then they write hardware that can't talk to each other. So I don't know if that's that answers your question. um, Yeah. So Raghav's question was, I meant logic functions and the ALU. Oh, so yeah. So the what instruction set the ALU might support is completely dependent on the instruction set. ARM will have certain operations like AND or XOR. Intel will have a different set of instructions. The AND gates, NOT gates I was talking about were more fundamental building blocks. So any multiplier, adder, anything that you build, ALU or the instruction fetch or whatever block you're writing, it'll eventually be an AND or XOR NAND gate. Okay, I'll move on to the next thing. So um, I worked for Connexent for about 3 years. After that, I moved to a company called Atheros, um, where I essentially built algorithms for improving the performance of Wi-Fi routers. Um, and so the problem, so Wi-Fi routers have, of course, have a lot of algorithms that run on them. For example, if you have a Wi-Fi router and a mobile phone, the Wi-Fi communication between them can happen at different data rates. So you can choose to send, or the router can choose to send a packet at 100 megabits per second. It can choose to send it at 200 megabits or 300 megabits per second. Then there's a whole range of data rates at which it can send a packet. But depending on um, how high speed the data rate that you're sending the packet on, there's a probability of success that the receiver will correctly receive the packet or not. So if you send it at 300 megabits per second, um, you may uh, you may have only a 30% chance that the packet will actually reach there. Whereas if you send it at 100 megabits per second, there might be a 90% probability of success. And these and based on these probability tables, you have to choose what is the right data rate for you to send the packet at that time. So for example, in this case, if you send a packet at 100 megabits per second, but it only reaches 90% of the time, you'll have an effective data rate of 90 megabits per second. But with 200 megabits per second at a 60% probability rate, you might get a higher net throughput of 120 megabits per second. So even though you're sending or at 300 megabits per second with a 30% probability, you may only end up with 90 megabits per second net throughput, because 70% of your packets will get lost because they didn't successfully get decoded by the receiver. So even though you're sending packets at a higher data rate, your effective data rate may be much lower. So there are all sorts of algorithms that are running in the background to choose what is the right data rate. And this data rate may depend on things like how many other Wi-Fi devices are communicating at the same time, how far is the router and the smartphone from each other. So there's all sorts of complications in deciding the right uh, data rate to transmit at. So a lot of the work that I did in Connexent was around in Atheros was around uh, algorithms that help you pick the right data rate to uh, help pick the right schedule. So, for example, a router may have uh, packets queued up for sending to the laptop, to your smartphone, to your TV, to your Alexa device. So there might be packets coming from the internet, from your wide area network, or from your cloud, that are going to all these different devices in your home. What should be your scheduling policy? Which device should you first send the packet to? Because the router can only send one packet at a time, so it has to choose whom to send the packet to in what scheme. And depending on that, you may get different performance. The route the You want Netflix, if you're watching a movie, you want Netflix buffers to never underrun. So you may have a different scheduling algorithm, or you may want to prioritize video traffic or voice traffic over, say, FTP or data download traffic. So a lot of the algorithms around scheduling, fair scheduling, those are the kind of things I worked on. So when you kind of study hardware, when you study electronics uh, and communication systems, right? You don't always end up designing sort of chips. You may be designing algorithms also, because some of these at the lowest level in the hardware, there's a lot of algorithm work happening, and so I got a chance to work on a lot of these algorithms during this time. A lot of the work that I did was also to take these algorithms and implement them in the Wi-Fi drivers. So that's kind of your firmware or low-level software, where you take these algorithms and modify the driver to try out different retransmission or data rate selection algorithms, and you see the impact on the performance in a real home or in your test environment. It's also a time when I got to interact with a lot of customers. So I used to visit customers in Taiwan, Korea, and Europe to understand what kind of applications they're trying to run in the next generation of in the next generation of routers. How would they like to sort of make these trade-offs of voice traffic needs to be very reliable, but can that happen at the expense of video or so a lot of this work was also kind of interacting with customers to understand what kind of algorithms they'd like to see on their routers. I'll take a couple of more questions. According to your experiences, what makes hardware different to other tech branches? I think hardware engineering is, to me, it's been a lot of fun. It's very challenging work. It's very sort of demanding. It makes you think. You have to learn a lot about all sorts of things. You need to learn physics. You need to learn software. Uh, uh, you need to learn a lot of different aspects to it to actually be a good hardware engineer. um, it's There's still a lot of innovation happening in hardware as compared to, say, civil engineering or chemical engineering. I mean, if you look at these days, a lot of people are building AI chips. People are trying to build chips that run on minimal amount of power. Just 5 years back or 10 years back, having a Bluetooth headset that could just fit in your ear and was so small was impossible to think of, because these chips used to consume so much battery power. But over the last few years, the battery power has come down so much that your iPods, they're so small and you can barely even make out where the battery is. And a lot of that is happening because hardware is progressing at such a fast rate. So I think hardware design, one of the coolest things to me about hardware design is that there's still a lot of innovation happening, and there's still so much innovation still to happen. So if you think about robotics, AI, and how it'll change the world, a lot of that will happen on the back of hardware, right? It's not just software that'll enable all these new applications, but uh, do you there's so much more sort of stuff to be done in terms of chip design, in terms of hardware design, to enable all these AI applications. What has helped you get into hardware, and what advice would you give someone to set off in a similar direction? So I think, um, I mean, obviously, getting a engineering degree in electronics helps you get into hardware. So I would say that is sort of one of the fundamental things to get into a career in hardware. But if you just want to dabble around, I think the Arduino platform is a very, very interesting platform to start to build stuff. You can build some simple applications around an Arduino, understand different types of sensors, plug them into the Arduino, read the data sheets or the programming of those chips, and you can start to build stuff even while you're at school. Um, what are the kind of assumptions inputs to these algorithms for wireless routers take? Um, so These algorithms are essentially running on the router. They're looking at all sorts of things. They're looking at the environment. They're measuring. For example, I sent a packet. Did it actually reach there? Did it Was it received accurately by the receiver or not? If it was, the receiver will send you back an acknowledgement. So you're measuring, for example, what was the probability of success of transmission. You might be measuring how many packets are there for different devices that are lying with you to transmit. You may be measuring things like power of receiving a packet. So you've sent a packet to someone, you might be measuring the power at which you receive packets from that other device to estimate how far it might be. So there's a lot of inputs that are there within the router as it's running the software to measure things that can go into these algorithms. What are the differences between modern broadcasting technology and traditional methods in terms of data transmission? I think, okay, so I think if you look at traditional methods of data transmission, it depends on what you are calling traditional. Uh, so traditional could mean analog module like AM and FM, what you use in your car to listen to music. These were all one-way communication. They were analog in nature. Um, Modern communication networks from satellites or cellular communication is all digital, which means that you are, for example, in an FM network or an FM transmission, you would take the analog waveform of the music and just transmit it. So if there's any noise added, then the music you listen to would be noisy. In digital communication, you take the waveform of the music, you convert it into a digital waveform, you break it into the bits, zeros and ones, and then you transmit it. And then you can add things like error correction, retransmission. So even if there is noise and you lose the packet, you can sort of uh, recover from that. So a lot of communication has become digital now, and that has helped the quality of transmission improve. And I mean, you hear about 4G, 3G, 4G, 5G. All of this is happening because you have digital communication, and a lot of that communication is happening at higher data rates. Also, because the chips that are the transmitter and receiver of these signals, they are improving in their capabilities. So not just our sort of CPUs improving in performance, but even these uh, what we call modems, the transmit and receive chips of communication protocols, they are improving in performance. You can pack more and more transistors into them, so you can do more and more complicated math to recover those electromagnetic waves and process them. So you can do higher data rates because of that. So the hardware underneath that can process more and more data, that can run more and more complicated algorithms, are helping improve the performance of these communication networks and push to speeds like 1 gigabit per second on your phone, because now the phone's modem is so much more powerful, and it can do a lot more processing. What websites, communities do I follow to stay up to date with hardware development? I end up staying current because of my work, but I think Reddit may have a lot of stuff. I don't have much guidance on this. I would say just Reddit might be a good place to get going. Can you explain the general concept of how a network switch works? This is kind of tough for me to explain in such a in such a format. I'd have to do a lot of whiteboarding and stuff, and it would have to be more interactive. So I don't think I'll take this question. Sorry. Okay, so the next project I did at Atheros Qualcomm was actually to design the chip architecture for Wi-Fi routers. So um, your Wi-Fi router that you have in your home, the TP Link or Linksys or Asus router that you have sitting in your home actually has a chip inside it, which has a processor. It has a communication modem that transmits and receives packets. It has chips that communicate over Ethernet. So packets may be coming from your DSL modem to the Wi-Fi router over Ethernet. Then the packet has to be converted from Ethernet format to Wi-Fi format, and then all these algorithms that do transmission have to run on this router to send the packet out. So part of my job was to uh, define the architecture of these chips. So because I'd spent so much time building uh, the firmware, the software that runs on these routers, and I had a deep understanding of the hardware, I was able to define the architecture of these chips. So, and a lot of that is trade offs. So, for example, you may want to put a more powerful processor on it so that you can deal with more packets per second, or you can run, uh, say, you could connect a hard disk to your router and store data on your Wi-Fi router, right? But a lot of these applications need processing, and the more powerful the processor you put on it, typically that means that it'll also burn a lot more power. So the chip will heat up, and if it heats up, you have to dissipate that heat. So you have to put a heat sink or a fan. So there's a lot of trade-offs involved in building these chips. So, like I said, if you make the chip too, if you're running it at a much higher clock frequency, or it's able to do many more operations per second, or a lot more sort of instructions per second, then it also means that it'll burn more power. You have to deal with that heat dissipation. There are also standards that say that a Wi-Fi router should not consume more than so much power, because it's energy inefficient. um, and also, as you make these chips more powerful or more performant, the cost of the chip goes up. So the consumer may not want to spend so much money on a Wi-Fi router. So you have to trade off between power, cost, and performance of these chips. And so my job was to spec the chip at the right processing speed, at the right memory bandwidth, and sort of design the architecture of the chip so that it fits the right envelope of power, performance, and uh, cost. This is, of course, very interesting work, which you get to do if you've learned like a lot of different things. If you've learned, hardware, software, a lot of different things, like the software that runs on routers. You have to really know a lot of different things, and this is typically in our field called systems engineering. Um, so a lot of this is is interesting work because it involves multiple facets of engineering from different parts of the design. There's another question: do you believe ARM will eventually dominate the mainstream PC world and perhaps replace x86? This is tough for me to say. ARM is getting in there. You are seeing laptops today with ARM as well as server chips. Um, it's picking up steam. At the same time, there's another competitor called Risk Five or Risk V, which is coming in, um, which is a open source instruction set, and a lot of people are building chips for that. So that's also picking up steam. But yeah, ARM is definitely a key player in this going forward. Is ECC, I guess you're talking about error control codes, just an algorithm or implemented through a circuit on memory modules? So, error control codes are used all over the place. They're used in when you store data, they're used when you transmit data. Um, Typically, it's an algorithm, but you implement that algorithm through a circuit. So, there's error control codes have a certain amount of math involved, right? So, you do that math needs some hardware to run on, right? And that hardware can be a processor. You could be writing, C++ or assembly code to implement the error control code which will run on a processor, which eventually is also running on certain gates, right? Every processor has AND gates, NOT gates. But that's typically a slower way to do it. If you want to do it faster, then you'll just take those algorithms, write them in Verilog, and then compile them into the set of gates that you want. So that'll actually be more power efficient, and a lot of places where you need to do error control codes on very high speed data, like if you're transmitting packets at a very high rate and you need to implement error control codes on those, then you will do it in dedicated hardware or dedicated circuits and not through a processor. Um, how do you recommend getting into systems engineering, particularly for hardware electronic system? Is it something that can be gotten into at entry level? I think systems engineering is an area that you get into by sort of working on different things. So, my path to system engineering was that when I started my first job, I was very curious. I used to go to my manager and say, I want to work on writing Verilog code. And he'd say, okay, next project, you can try that. And then I'd learn that. And then I'd say, after a few months, I want to go design a PCB. And then he would let me go work on that. And so I was fortunate to have a manager who would let me work on different things. But I think the most interesting, the easier, the most straightforward way to get into systems engineering is to actually work on all sorts of different things. If you worked on all these different types of algorithms, hardware design, software design, PCB design, you will eventually become a systems engineer because you would have worked on so many different parts of the system. So you will learn how to build uh, complete systems. Okay, the next sort of in 2013, I quit Qualcomm. I wanted to do a startup, but in between, uh, I helped out this startup called EasyTap, which was building a payment device. So sometimes when you pay for things, in the old days, taxi drivers and Amazon courier deliveries would use these EasyTap devices. There's another company in the US called Square that builds devices like these. There's basically a credit card reader, which at that time used to be connected to the phone using the audio jack. And later, of course, Bluetooth became much more prevalent. So everything happened over Bluetooth. But in 2013, the device still talked to the phone over an audio jack. And um, I basically built the communication protocol for this company um, to communicate between this device that's reading the credit card and the smartphone. And the way we would do that was, if you wanted to send a zero or a one, you would send a sine wave of different frequencies. So if you wanted to send a one, you would send a higher frequency sine wave. And when you want to send a zero, you would send a lower frequency sine wave. And so if this device was sending these sine waves, the receiver, the smartphone would have an Android app which would open up its mic and start to record this waveform. And then after it had recorded it, it would then try and decode this by measuring the frequency of the sine wave. So I wrote this signal processing algorithms to decode this sine wave back into this sequence of zeros and ones. It seems a little simple when you see this wave, but what happens is that a lot of noise can get added, because anywhere where you have wires and you're transmitting a voltage over it, there will be noise. So this waveform doesn't look so clean. The other problem is you don't actually know when the bit starts and where it ends. So over time, you're just detecting the edges of the bits can get complicated. So a lot of uh, the algorithm design of this was done by me, and then I implemented them both on the embedded processor and the Android app for this company. It was kind of interesting to do. It's a much simpler communication protocol than what's used in cellular communication, for example. But this is the fundamental way a lot of communication systems work. So it was interesting to build a very sort of basic communication protocol uh, from scratch. So I worked on this for about 3 months. It was an interesting little project. Um, from here, I actually started my own startup. This was to build industrial IoT. So we had built a complete stack to monitor factory processes. So we would build devices that would connect to sensors. They would transmit all the readings of these sensors over a Zigbee network. Zigbee is a local area network like Wi-Fi, but it's better for industrial applications because it's much more long range and easy to build. Um, and it Wi-Fi can get tricky because over longer distances Wi-Fi doesn't work so well. Um, the so we actually built the whole end-to-end stack. The startup, we had about 5 people uh, working in the company, and between us five we built all the PCBs. We built the Zigbee protocol stack. We built a gateway device that would take these packets coming over Zigbee and then send them out over Ethernet or over a 5G or 4G dongle connected to the gateway. Um, and then we built sort of this cloud stack for analytics. So your standard backend, front end servers that could do all the analytics with all this data. And we wrote code in C, C++, Python, JavaScript, and all your different sort of programming languages. Lots of different frameworks, Zigbee protocols. There's this protocol called OpenWRT that lets you sort of take control of a Wi-Fi router. So we built our gateway using a Wi-Fi router, and we added some Zigbee devices onto it and used OpenWRT. We actually deployed in a couple of factories in Hosur. There's a factory for Titan. Titan is your watch manufacturer, and we used to do some industrial safety monitoring for them, and also paint factory to monitor paint production. But we really couldn't find a scalable business model at that time, and we couldn't find the right product market fit, and we shut down in a year. But it was very, very interesting work. In a year, we achieved so much in building like this end-to-end stack of hardware and software. Um, and I think this was one of the best learning experiences for me, to both technically and sort of learning how to do a startup or how not to do a startup. Um, of course, 2014, then my startup sort of folded up, and I joined back at Qualcomm. I started working for this research group that was working in virtual reality. Um, this was again a very interesting project. So we built a 360 video camera. So if you've seen this GoPro camera, it's basically a 360 video capture device. So you have uh, what is called a fisheye lens. So fisheye lens is a lens that allows you to capture 180-degree field of view. So um, if you take two fisheye lenses, then you're basically capturing everything around you. So this is the view from one fisheye lens. This is the view from the other fisheye lens. And the team that I built at Qualcomm was really the first time anybody put together a video camera on an embedded platform that could stitch these two views of these two fisheye lenses into a single 360 view. And we were doing it live, and you could stream it to a VR headset and watch the live stream coming from this camera. So this was, of course, a lot of image processing algorithms, and implementing those image processing algorithms on a embedded platform so that you can do it real time is very challenging, because at that time most companies were running this on a PC or a server, and they would do it offline. They would take the two, MPEG files, transfer them to a machine with a GPU, and then run the algorithms. And we were able to do it live, which means that you're running these algorithms at a very high frame rate. So you have to really optimize your code. You have to optimize your algorithms to be able to do that. And finally, we integrated this onto a drone. The drone was basically flying in the air. So we demoed this at CES, which is a trade show in Las Vegas in 2017. And this drone is flying in the air. It has a 360 camera built on it, and the same Snapdragon processor that you find in your smartphone, it was doing all the flight control, all the flight uh, autonomous flight control, as well as running the 360 video capture and streaming that capture live to VR headsets. So people could watch the 360 view as if they were sitting on top of the drone. So this was again a very interesting problem that I worked on. The last one was the last project I worked on with the VR group was sort of building algorithms for these VR headsets. Uh, so today, Oculus Rift is a sorry, not Oculus Rift. The Oculus Quest is a VR headset that actually uses Qualcomm chipsets, and um, the VR headset itself needs a lot of algorithms because it's a very uh, challenging thing to make people believe that they are in a virtual that the virtual world is as good as real. So, for example, a very interesting problem in this whole thing is what we call motion to photon latency. Uh, Essentially, in VR headsets, when you move your head around, the VR headset has to estimate how much you've moved your head and then refresh the view of the displays in the VR headset to reflect the view of the world if you had moved your head. So, for example, if I'm looking straight, then the view that is being rendered is of my laptop. But if I shift my head 90 degrees to the left, then the VR glasses have to show me the world that was 90 degrees to my left. But you have to do that within milliseconds, which means you have to detect accurately how much a person has moved his head. You have to send that information to the game engine, and the game engine has to render that new view for that new headset position, and then you have to bring that view up uh, on your headset. And so my team was working on these algorithms that allow you to do all this in a matter of milliseconds, because if you take more than a certain number of milliseconds, then you start to feel nausea because the view in the headset will sort of lag your head movement. You move your head, and then half a second later the view will update. That is very noticeable, and you'll start to feel nausea. um, so yeah, I can start to take questions. I didn't have more slides. I think Yoda has a question. How do you think the emergence of cloud and cloud products will affect the interest in hardware? So um, I think the mm, there was a time when I felt that the emergence of smartphones and cloud kind of slowed down innovation in hardware, because sort of building hardware, releasing it, scaling it to the masses is much easier than building hardware and scaling it and releasing it to millions of people. But I think you'll also see that as cloud and cloud products come out, there's a lot more demand for hardware, right? And a lot more challenges in hardware. So um, you 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 look at all the stuff that's happened in AI, right? So there's so much happening in computer vision. and OpenAI and language processing. But if this truly has to like go from being a hobby to mainstream, you will see that hardware will have to play a big role in this. I mean, there is no way that all this AI will become, 100 times more adopted without fundamentally hardware improving with it. And the other thing is that as applications of AI come out, you'll see lots of new hardware innovation as well. So, for example, uh, can you run a camera that can uh, detect things happening around you, make inference or make predictions on what do object detection or things like that? But can you do it with a camera that runs off a tiny battery and runs for 10 years? Today you can't. And to do something like that, you need to design more and more complicated hardware. So there's, I think, hardware and software go hand in hand. You can't do innovative software without doing innovative hardware. Um, did the work from this project eventually develop into the Snapdragon XR2 platform? Yes. So a lot of the VR work that we did does end up in product. Um, and a lot of the features that the Snapdragon platforms have come out of research groups like mine that do research in virtual reality and other areas. So it's absolutely does impact our products. That's all I had in terms of slides. If there are any other questions, maybe we can keep it open for another couple of minutes.
Okay, so guys, please feel free to ask any other questions. Also, sir, I had a question myself. Can I ask?
Sure.
Okay, so, sir, right now, in the current years, from 2020 onwards, we had been facing a global chip shortage or the semiconductor shortage, in other words. So, how has the semiconductor industry been dealing with that? Since you are a person closely associated with this industry, so I thought it would be right to ask this question.
Okay, so the companies I work for typically are fabless, which means that we actually don't fabricate our own chips. We design the chips and then they go to fabrication companies like TSMC, Samsung, or Global Foundries to get manufactured. So I can't give you like an accurate view of this, but I think what has happened is multiple things. I mean, because of the COVID situation, supply chains were disrupted. Now supply chains are improving, so factories are better at being able to uh, sort of meet the demand. Also, a lot of things. What companies will also do is they'll try and make their designs, their chips designed so that they can get fabricated in different fabs. So if one fab has a shortage, you can go to a different fab and get it fabricated as well. So that's another way that uh, semiconductor companies deal with shortages. There's another question from Raghav.
Yeah.
Do you think hardware is behind due to the extreme cost involved in fabrication, or is it the lack of number of people associated with the hardware field? So I think it. I don't know what you mean by behind. There's nowhere else to compete with, right? Hardware is hardware, but if you mean like people wanting to go into software more compared to hardware, or speed of innovation being different, I think fabrication cost is a consideration. I mean, to start a startup in software requires two or three people to get together, uh, pick up a laptop and write code, right? At least to get started. And over time, your costs scale as you get user adoption. the barrier to entry in hardware can be much higher. So, like I said, to fabricate a chip, you need to spend 10, $20 million, right? And you need a huge team of people to do that. So, it does take a lot more effort to build chips. Uh, but there are a lot of startups, not just in chip design today, because AI uh, is sort of spawning a bunch of chip startups, but also there's a lot of startups in building devices on top of chips. I mean, to be building startups in hardware, you need not just be building chips, you could be building devices using that chip. So you could be building the next Wi-Fi router, which has some super cool functionality nobody else has ever thought of, right? And that doesn't need you to fabricate new chips. It is still a little more complicated than writing software, but it's not prohibitively expensive to prototype certain hardwares, or to build like a proof of concept Wi-Fi router or something. It's not that expensive to do. Um, how do you think we can increase the literacy in terms of hardware in India? So I think hardware in India is actually quite a prevalent field. I mean, there are lots and lots of people who are in the area of chip design. Um, I think the normal, like, layman doesn't get to know about the work that's happening, but there's definitely a lot of work happening in India in terms of hardware design. And in terms of semiconductor design, I think India is probably number two uh, in terms of how much design happens in the world in India. Um, what kind of hardware research is currently important for VR applications to make them usable? Is the emphasis on improving hardware flops, software optimization? So there's actually, I mean, VR I think is still at its infancy stage, right? I mean, you would want VR devices to be 100x better than what they are today. I think it's still very, very basic in terms of what can happen with VR versus what happens today. So, I mean, to be able to get to that 100x performance, you're going to need to do all sorts of different things. So, for example, today VR headsets will display at, say, 60 hertz refresh rate, right? You want to be displaying at much higher refresh rate so that so that it feels more real. You want to be able to get many more megapixels in that display, which means that you not only have to design better displays, but the processor or the graphics processor that is creating these images also need to be able to handle building a much higher resolution display. So to drive that very high resolution display, you don't just need a very high resolution display, you also need a processor that can generate content at that high resolutions, right? So hardware has to improve in all sorts of ways. There is a lot of software optimization as well. So, for example, to make something believable in say augmented reality, you have to have the right kind of shadows. You have to have the right kind of lighting on the object. You have to track the real world much better than you do today. There's a lot of software algorithms involved in that, right? Um, so there's tons of work to be done in virtual reality, and even more in I think augmented reality. I mean, even today when I've tried out augmented reality headsets, it's very sort of disappointing to see how uh, how limited the field of view is, how sort of jarring the differences between the real world objects and the virtual objects that are being placed in that real world. So I think there's tons of work to be done in virtual reality, augmented reality, which is all across the board, not just hardware design, software optimizations, as well as sort of algorithmic work. Um,
And so we have another question that what is the thing that which you once thought was impossible in hardware but eventually has become a reality?
I think this is, I think one of the things that I've always felt bad about is that I'm not a visionary. At every stage in my life, I've always felt that this seems like a dream, right? This seems impossible. Like, uh, when smartphones first came out, they were bulky, they were uh, the battery life used to be so little, and then people started talking about smart watches, and they said, oh, we're going to take all this functionality that you can do on a phone, right, which has this big a battery, and I'm going to shrink it to this smaller form factor, and the battery will be tiny, and it has to last 3 days or 5 days or 10 days. And it's like crazy to think about it, but the reality is that Moore's law catches up, and people make make things that seemed impossible happen all the time. So I think one of the key things for me has always been battery life. So for almost every device that people dream up today and say, oh, we'll have this in 10 years, I'm like, there's no way the battery life can sustain it, right? But eventually they build it. So even like Google glasses, right? You think about Google glasses, there's like this little display, lots of processing, and of course there's HoloLens and all sorts of things today. But all these VR glasses and AR glasses are so bulky, and a lot of that is because the processors are big, they're burning power, the batteries are inefficient. um, and I think this is again one of those things where I feel, hey, I don't know if VR glasses will ever reach that point where they're comfortable and they're like really plugged into you, where they're not intrusive. But I think it will eventually happen because people build stuff, they innovate and build stuff.
Sir, I have a
um,
question.
sure, go ahead.
Yeah. So, sir, my question is like, since you had been involved in like product designing and all of these things, so what do you think is more important for designing such things? The accessibility and functionality, or the cost, costs and all that, all those things?
So those things go hand in hand, right? I mean, it is always a trade-off. You cannot build, I mean, in the beginning stages, customers will pay extra to get functionality, but eventually costs get driven down. So when you design chips, you have to keep both things in mind. You have to sort of see how you can get the functionality you want in that cost envelope, right? You may
Yes.
sure in the first product maybe you won't worry about cost, you won't worry about heat dissipation or those kind of things, but eventually you have to bring in those factors and then uh, build keeping that in mind.
Okay. So, yeah. So
Uh,
we
up,
have another question.
what
Sorry.
are some of the upcoming tech or companies that you find interesting? I mean, of course, in AI, there's a lot of interesting stuff happening in GPT-3 or Stable Diffusion, and I guess you guys follow that just as much as we do in the industry. I think AI in computer vision and natural language processing is advancing at a very fast pace. It's happened because there's so much data that social networks and smartphones have made available, right? There's so much data around images, tagged images, and speech and things like that that researchers have access to. But I think even today, when you try to apply the same machine learning or AI techniques to new fields like medicine or say fluid dynamics or uh, designing a car, right? AI is nowhere near what it is nowhere as advanced as it is in computer vision or natural language processing. And I think that to me is the next frontier. uh, Being able to apply the same kind of almost human intelligence that machine learning algorithms have had in areas other than computer vision and natural language processing. Like, will the next set of COVID vaccines be discovered through AI, right? And in these areas, it's very interesting because one, data sets are not easy to come by. You don't have millions of samples of what happens when you inject someone with some random chemical formula, right? But the other piece of it is that you don't have, when you build AI for computer vision or natural language processing, when you see a picture and you say, oh, this muffin looks like a dog, so yeah, the neural network made a mistake. It's easy for layman to understand. Like, if you're a layman who just knows AI algorithms, it's easy to understand why the machine made a mistake. But when you're dealing with things like biology or medicine, to understand why the AI made a mistake or how to make it better, you need to understand not just the AI algorithms, but also medicine or biology or chemistry. So I think that will really be the next frontier where people will learn to apply this kind of technology to new areas, and it will need people who it will not just need data sets, but it will also need people who are multidisciplinary, who know, who understand AI algorithms, but also other areas like biology, chemistry, engineering, or accountancy, or whatever. So I think that's really the to me, like, the next frontier in AI. What's your opinion on imbibing hardware into human bodies in order to be one with the internet? I have no clue about this. Sorry.
Yes,
Would I?
because like Elon Musk has been trying a lot of different things, so those kind of questions do pop up in mind. So those are there.
Yeah, I think the tech will get there eventually. I mean, it'll be there maybe in 5, 10 years, whatever. There'll be, of course, always these questions of ethics. The cool thing about engineering is you build stuff without thinking about ethics, and you let the ethics sort itself out later.
Yeah,
I mean, even with like smartphones, people talk about, is it ethical to have smartphones? Is it ruining our lives? Is it too intrusive? Are there privacy concerns? But engineers don't worry about these things. They just build whatever they can dream up of, right? And whatever is technically possible. The ethics will follow later. And so I think uh, as an engineer, you just build stuff because you can. And I think it's very cool that we can build stuff that will connect into the human body, right? I mean, already there are people building continuous glucose monitoring chips that sit just on your skin or just inside your skin, and you can do monitoring of your blood all the time. And
yeah.
I mean, how far
It
is
is
it to
like,
just monitor your brain waves?
yeah, like because the culmination of imagination leads to new inventions after all.
Yeah, I mean, the jobs of engineers are to build stuff you can imagine, right? And
True.
then worry about ethics later.
So we have a related question again. How will technology make our lives better in the next 10 years?
Um, it's an interesting question. I think things will change for sure. I mean, people talk about AI and how there will be job losses, but I think people have talked about sort of that happening ever since the day. I mean, engineering has always done that, right? Many years back, you used to have horse carts, and then cars came along, and things became more efficient. People lost jobs. People who took care of horses lost their jobs, but new jobs were created, right? People
New
started
jobs.
becoming mechanics or auto engineers. um, I think the same will happen with AI. AI will change the way we work. It'll take away more mundane jobs, and it'll make things more creative, more challenging for humans. So definitely, I think AI is one of those big areas that will impact human lives. There's a very interesting talk by or blog by Anderson and Horowitz, which is a VC firm, on all the impact that autonomous cars will have. So it talks about how once you have autonomous cars, you will no longer need parking spaces, because when you go to a restaurant, your car will go act as an Uber while you're eating your food, right? And it will unlock so much urban land right? Or insurance companies will change suddenly because autonomous cars won't have as many accidents as humans have. So I think autonomous cars are another sort of big technology impact that will happen over the next few years, and in ways we can't imagine. I would highly recommend watching that Anderson Horowitz blog on autonomous cars. But yeah, I'm not a visionary. I'm not the kind of guy who sort of says this is what is going to be cool in the next few years. I like to watch more than predict. But yeah, AI definitely. I mean, these are trends everybody knows. AI is going to be big. Autonomous driving will be big.
Another question I want to ask, sir, before like we reach the conclusion, I wanted to ask like if like related to products only, like if you have designed a product, should it be just about a new idea or something, or like it should focus on the target market as well? Because like what many entrepreneurs do is that they focus only on their ideas and ignore the target what the target market thinks, and it messes up a lot of.
Yeah, so I think hardware startups are a lot like software startups in that sense. I mean, you have to build a minimum viable product, which is based on your idea, right? So it may be something crazy you thought of, you thought was going to be very useful for people, right? So you build a minimum viable product, you take it out there, you meet customers, you meet people, and then you realize that, hey, what I thought was going to be cool is not cool for everyone, or they're not willing to pay for this. And then you pivot, right? You build something different, or you change your product a little bit based on user specs. So hardware is a lot like software in that way. You sort of build it, uh, and you try and sell it, and you see what happens, right? And in fact, a very smart venture capitalist once gave me this advice. He said, if you're thinking of building, say, the next cool Wi-Fi router, right, that has some amazing features that nobody else's Wi-Fi router has, first go and try and sell some basic Wi-Fi routers, right, and understand the market. Or build your product in a way that you don't sink in too much engineering cost. Build really a minimum viable product. Try and sell it. See how people take it, how they accept it, and then pivot. Uh, because I think, yeah, unless you're Steve Jobs and can sort of predict what people want, most people have to build, try, pivot, and sort of build again.
Okay,
Cool.
beautiful. Yeah, I
I
think
guess
we
I'll
don't
take
have
one
any.
last question, but I don't have much time beyond that.
Yeah, I guess since there are no other questions, let's uh, now conclude this session. Thank you so much, sir, for
Sure.
giving this wonderful talk. And I hope all the viewers enjoyed this session. And stay tuned for more amazing stuff. Exun,
Thanks,
me,
guys, for all
Dr.
your great questions. It was
Thank
nice
you so much, sir.
interacting with all of you. Thanks. Bye.
Thank you so much.